Hi everyone, I am Elif. In this video, I will explain the questions and answers of exercise sheet 8. And in exercise 1, we have 5 statements and we want to decide if they are true or false. So, well, the first statement claims that there exists an element f in the dual space V star such that it is not vanished at any vector x in the vector space V. So this statement is false because if we consider the zero vector, if f of x is different than the zero of the field, here note that V is a vector space over K, then f doesn't belong to the dual space. We basically use the fact that if f is linear, then f of 0, the image of 0, should be 0. So the statement is false. Okay, in the second statement, phi denotes a bilinear form, and it is claimed that any matrix satisfies this equality which is defined with respect to the bilinear form. So here note that phi doesn't have any spatial property like being positive, definite or symmetric. So to see that this statement is false, we simply consider a counterexample in R square. And in this counterexample, we consider bilinear form, which is defined by this matrix, or algebraically defined by this equation. And particularly, we set matrix A with these entries. So on the left-hand side, let me call it M. We have this equation. And for the right-hand side, we have different equation. So simply to complete the counterexample, we may particularly consider 0, 1 and 1, 1. So by these spatial choices, we obtain that these are not equal. So this statement is false. So for this question, I want to recommend you what happens, when do we have this equality? For which phi and for which A we have this equality, and you may also think about it. And yeah, for the third statement, I had to send a correction. I'm sorry for that. Because, before the correction, n was missing here. But I wanted to ask if or not the Hölder-Minkowski equality holds only when x and y are collinear. So since phi is not given as definite, this statement is false, because simply you may consider the zero form. This is obviously positive by the definition because of this equality, but it is not definite. So always we have this equality, and this equality is independent of the choice of linearity or collinearity of x and y. So this statement is false. Okay. Statement 4 claims that the group of the matrices with determinant 1 is a subgroup of the orthogonal group. So actually, to be subgroup, it should be the orthogonal group, but otherwise the statement is not true. Counterexample can be given by this matrix. Obviously, this M belongs to the H. But MM transpose is not identity. So the statement is false. Okay, the last statement is the only true statement in exercise 1, and it contains two parts actually. Namely, let M be a negative definite matrix. That means this real number always strictly less than 0 for all non-zero vector. And first we want to see that M inverse exists. And in the second we want to see that M inverse is also negative definite. So, okay, we prove the first part by contradiction. That means we suppose that there exists non-zero x such that M times x is 0 vector. So that means M is not invertible. So this implies this real number is going to be 0 for non-zero x. This contradicts with the definite of, it contradicts to being M definite. So that means M inverse exists. And for the second part, we know that from the first one M is invertible. So we may consider an isomorphism which is defined by M. That means for any non-zero vector y, we may obtain x by this equation. So simply we plug in this equality in this part. Transpose M inverse and M of x. So this is going to be identity, and x transpose M of x. This real number, this is a real number, so the transpose is transpose of this real number is going to be itself. And by the assumption, we know that this is negative, and this completes the proof. And yeah, hopefully you didn't answer this question simply by proposition 4.20, because in this proposition we need this symmetry, but in this statement there is no information about the symmetry. And yeah, thanks for your attention. If you see any mistakes, don't hesitate to tell us. Hope to see you in the next video, and bye bye.